Good morning. So today we will see the PSC bridge. Especially this is a simply supported box girder bridge. We'll make it, and including the loading part, that's the live load as per Euro standard, as well as the precise load. We will see on that. Now this is the software interface. So the introduction about this is not required because you're already familiar with the interface of the software. Now I will directly generate this geometry and loadings over there. Now you can see the first, I'm just save the file. Giving the name as box girder. I saved it, so the program will automatically save the file. I set my preferences every 1 minute, so automatically it will save for every 1 minute. This is the plan view. First, I'm creating the geometry, node and element. Create node. First node at the origin point. So it is 5 times I'm copying for 5 meter. So this many nodes is created. This is the node number which is activating in the screen. You can see the 6 number of nodes. And then next is a element, create element. And as of now, we have not created the node and material and cross section. So now we can first connect the nodes, that is node from 1 to 6. Click apply. Now you can see the node is connected. Now in our work, we can see the 6 node is created and 5 beam elements are created now. Now 5 into 5, 25 meter total span. And then we have to define the material property and cross sections. That is a go to properties, material, add. This is the material database. As we are going to create a PSC, so I'm selecting the material is a concrete. And Eurocode as per C3545, and the name I'm given as, okay, same name, it will be taking it. One is the concrete properties, another one for precise steel. This is a steel property. I'm selecting one material property in terms of steel for the precise cable. In actual state, the precise cable is a high tensile wire. So this property is different from the reinforcement properties. So generally, we can use the user-defined material property if you know the property of the section, which will be provided by the manufacturer of the precise cable. Now we will consider this property S355W is the material property for the precise cable. And the next is a section, the section property, add. Yeah. So as we know, the first one is the database and user-defined section, and the second is value type section. The property is the input now. And SRC, seal reinforced concrete, combined section, and PSC, tapered, composite, and steel girder. Now we are going to use the PSC type. I'm selecting PSC N cell type. I'm giving the name as N section. And the number of cell is 2. H1 is based on the reference picture. This is the reference picture. Based on this, I'm going to create the dimensions. H1 is a 2 meter. H2 is 0.3. H2 is 0.2. And H4 is 0.3. H5 is 0.3. And B1 is 10 meter. And B2 is 2 meter. Sorry, H5 is 0.3. Yeah. And then B3 is 0.3 and sorry, B2 is 0.3. Sorry. B2, the cantilever portion is 2 meter and B3 is 0.3. B4 top haunch is 0.2. B5 bottom haunch is 0.2. Again, outer web thickness is 0.3. And then select this CR calculation and torsional calculation is as per the automatic condition. And your offset command at the top. And this is my N section. Okay, this is my midsection. Add. I just added the first cross-section property and the second ID is automatically updated. Now this is my end section or the diaphragm section, which has to be the higher stiffness. So I am just making the thickness is H2 is to be 0.5, H3 is 0.3, H4 0.5, H5 0.5, and B1 same 10 meter, B2 is same 2 meter, and B3 is 0.5 meter, and B4 is 0.3, and B5 is 0.3. Outer web thickness is 0.5. So this is the cross section at the end portion we considered, and then click apply. So second section is added. So second section is supposed to be my end section, so I will change the name later. The next property is my taper section. I'm giving the name as end to midsection. Same PSC end cell type. I'm importing the property. This is our end section. Import. Another thing is a size J, J10. That is first section. This is the linear tapering, and offset is center top offset. Click OK and apply. So third section is added, and next is a fourth section. This is mid to end. Mid to end, I have to select the midsection property as I10. This is my midsection, and then this is my end section. Again, same linear tapering and Y and Z direction, and center top offset, and click OK. So we have four cross section. This is my end section. I'm just modifying the name. Fine. So now you can see this midsection, end section, end to mid, mid to end. Now I will just select this to end portion as my end section, drag and drop. It's modified over there, and this section is my end to mid. It's applied. Again, this section is my mid to end, modified. So it is, now you can see the taper section, and clearly this is a linear tapering. So this portion is it is defined. And next is a support condition. We have to provide the two bearings on each side. For that, I am just copying this two end nodes at the distance to the near the outer web, mid of outer web. So I'm going to the node and element and translate, and translating with the distance of y is 2.75. Y is 2.75 comma minus 2, because the depth of the section is 2 meter. It's copied over there. Again, one more time, this is minus 2.75 defined. Now in this section, I'm just copying this nodes one more time. That is your 0, 0, minus 2 meter. Sorry, minus 0.25. That's the bearing height. Now again, the structure and the bottom supports to be connected. That is by rigid link and elastic link. Let's see how to apply the rigid links and the elastic link. And this is the boundary conditions. First one, the rigid type elastic link. We have to define the master node and slave nodes. The master node, I'm selecting the node number 1 is the master node. There's a rigid body connection, and my slave nodes are the soffit of the girder. This is the nodes, and I can immediately copy on the rear side. That is your 25 meter, and apply. Now you can see the rigid link is created over there. Now you can see the rigid link is created. Next is we have to connect by the elastic link by the bottom node, that is your bearing location. That is boundary, elastic type. Internal type is rigid because we don't know the exact behavior of the bearing. So initially we have to consider as a rigid and then analyze and check the behavior. Accordingly, we have to design the bearing, and after the design the values, we have to replace with the actual values and analyze again. This is the general procedure. Again, this is copy at the distance of 25 meters so that I can connect these two nodes and these two nodes. So this is a elastic link and rigid link is created. I will just activate this elastic link also and rigid link also. Now you can see in the screen. Now next is this support condition. We have to define a support. The D all, that means the translation and X, Y, Z direction is fixed on the left side. On the right side, I release the DX direction so that I can achieve the simply supported conditions. Now I will see how support by direction. Now you can see the support which is applied on both the corners. Now next is a load application. So go to load, static load. First we have to define the load cases. That is our static load. This is a self weight. Load case name is dead load. Apply. SADL is dead load of component and attachments. And then pre-stress load. Load type is pre-stress. Add. So the three load cases added. The self weight load we are applying. Before that, we have to create the group for this because we are doing the construction stage analysis, so that the construction stage analysis will be applicable only with the groups, so that all the information about this model we have to connect with the groups. Okay, and here from the tree menu there is a group. Here I am making the group like a structure group. So this is the group name. First group name is a structure group. I'm giving the name as SG. You can give any name for that. Structure group, and then boundary group BG, and load group self weight SIDL, and pre-stress. Add. Okay. And next is I have to assign all the information with this groups. I'm just selecting all the node and element under the structure group. Drag and drop. It's assigned. Now it's under this group 14 nodes and 5 elements are there. Now the BG boundary group. I'm just selecting this nodes where I have applied supports and links, and just drag and drop. I have created only one group for this. It will automatically created. Now how we can cross check with that? Go to work, right click the support, go to table. Now you can see the group name is appear in the table. Similarly for elastic link, right click, go to table. It will, the last column is a group name. It is automatically assigned while you are doing the drag and drop. Similarly for the rigid link, right click, table. This is a rigid link 2. Rigid link we have, the group name is BG. And then the application of load. Now go to the load, self weight. Load case is self weight. Load group is also self weight. Z is vertical, so Z is -1, so that the self weight will be calculated automatically. And next is a superimposed dead load, that is your cross barrier load, that is considering as a element beam load. This is a beam load and element type. The load case name is SADL, and load group name is also SADL. This is referring from the eccentricity from the offset location is a local Y or global Y, because the straight bridge, the local and global is parallel, is similar. So for straight bridge there is no difference. So I'm selecting this member, and eccentricity is 5 meter because the total width of the girder is 10 meters, and giving the load information is minus 2.5 kilonewton per meter. Apply. And one more time is a minus 5 meter with the same load minus 2.5 kilonewton per meter. Apply and close. Now we can see the load which is supplied at the edge of the slab. And next is the pre-stress. For the pre-stress case, we have this one temperature and pre-stress. We have 3 steps. First, we have to define the tendon property. Add. So this is a tendon. I'm giving the name as a tendon. And we have 3 types of tensioning. That is your pre-tension, post-tension, and external pre-stressing. Now we are following the post-tensioning method. Material we have defined earlier. I am selecting the material and total tendon area. Here I have to select your standard strand diameters and 12.7 mm, 19 number of strands with 12.7 mm dia, and click OK. This is your total tendon area, and duct diameter we are considering 90 millimeter, and relaxation coefficient as per European standard for low relaxation because this is a high tensile wire. And then the ultimate strength, yield strength, curvature friction factor, wobble friction is as per the properties and the standard, and the anchorage slip is 6 millimeter is considered as per the standard. And click OK. So the first one, tendon property. Next is the tendon profile we have to generate. Add. And this is the tendon profile input data. And before entering here, we have to generate the cable profile in 3D. So I'm giving the name as T1. This is tendon, and this is the element number where you want to apply the pre-stress for. That is our 1 to 5. Input type is 3D, and the reference axis from the element because your coordinate is calculating from the element location. And now I will be opening one Excel sheet. Now you can see this is the Excel sheet. I'm just calculating the coordinates. The first coordinate is 0, 0, and next is the 1 meter. So this is 12.5, so total is 25 meter. I'm just calculating the coordinates for of the length of the bridge because then after that I can make it symmetric. And Z coordinate is minus 1 meter, the starting point, and second point from the minus 1 and point this is from this minus 0.05. This is my cable number 1. You can see this is the cable number 1. I'm creating the 3 cables. Pasting the coordinates, and this is my 1.25. Sorry. 1.15, this is 1.25. So the 3 cables we have created, now we will just copy paste the coordinates over in the table. Just paste it for the first cable, make symmetric. The starting point of the cable, that is profile intersection point, is element number 1, and then apply. It's applied over there. Now we can see, visualize the tendon profile point. You can see the cable over there. And second is you can change the name to T2 remove the existing coordinates and copy the second cable coordinates. Paste it, make symmetric, apply. Again, change the name to T3, that's the third cable. Copy the cable coordinate, delete the old one, paste, make symmetric, apply. So we have three cable coordinates now. Okay, we are seeing this one. And another way, the same number of cables I want to copy to the outer web. Now you can see this cable, copy and move, equal distance, that is your 0, 2.75, 0. Currently assigned element, apply, it's copied to the outer web. The same way, I am doing one more time 0, minus 2.75, 0. Currently assigned element, apply. So it's copied to the both the outer web. Totally we have 9 cables now. The name will be automatically created, like a T1 means T1 copy. Then rename you can do it later also. And next is the tenant priestess. This is your load case name and load group name is priestess. I'm selecting all the cables. If in case practically we are doing this cables by staging, if you are following the stage wise processing, then you have to create the number of priestess load group and load group as well as the load case name. Because in corresponding duration we have to keep on activating these groups over there. Now for here I'm assuming all the cables are stretching at one time. So that's why I created only one load case and one load group. And then my input type is a force type. I'm giving as a force, and your force value is in ton force. I'm changing the unit to ton force, and this is my both end jacking condition. I'm applying the 200 ton force on both the sides, and the grouting after one construction stage. And add, and previous load is applied now. Next is a moving load. Next, go to the moving load, select the code, Eurocode, traffic lane, add, and lane 1, lane which is 3 meter, eccentricity we are following 2 meter from the central line, but actual condition we have to calculate from the curve distance. And then vehicle load distribution within the lane limit. I'm selecting the point. This is my starting point. This is my end point. Apply. The first lane is created. I can say changing the name to lane 2 and removing the existing points. Now one more time I'm creating the things and apply. So 2 lanes is created. I think let me see. Second lane is 2 meter eccentricity, and the first lane is okay. The second lane, the eccentricity is a different one. It's supposed to be a minus 2 meter eccentricity. Okay. Now let's see the lanes. Now we have 2 lanes. Now next is a traffic vehicles. Vehicle definition, add standard vehicle. Load model 1 I'm selecting, and then load model 3 I'm selecting. Apply. So we have selected the 2 load cases. And next is a moving load cases. Add. This is the moving load cases. I'm giving the name as MBC. And load model 1 and 3 multi lanes. The load model 1, load model 3 for both the lanes. Select and click OK. This is completed now. And next is we have to do the construction stage analysis for the processing. So for that, before that, I have to apply the properties for the time dependent material. That is I'm changing the unit to Newton millimeter. And properties, this is a time dependent material property for creep and shrinkage. I'm selecting first one as a creep and shrinkage. Add. I'm giving the name as a C and S as per European standard. This for 45 Newton per mm square is the FCK value. Relative humidity is 70%. And notional structural size of member we have to calculate as per this formula. I'm entering as a 1000 millimeters. And type of cement is class N, and type of code is EN 1992 for concrete bridges. And age of concrete at the beginning of shrinkage is 3 days, because first 3 days is the liquid stage for the hydration process. So we are calculating after 3 days. And show calculation result. This is your creep coefficient, and this is shrinkage strain values. Click OK and OK. This is the creep and shrinkage function, and we have to define the compressive strength factors. So this is the compressive strength. Add. This is compressive strength factor as per European standard. This is 45. This is FCK plus delta F. That is your 47.5 roughly. So read the graph. This is the compressive strength variations, and click OK and close. Okay, next is the material link. This we are linking the creep and shrinkage function and the compressive strength factor with the concrete properties. Then automatically this effect will be considered whenever we are doing the construction stage analysis. And this is the construction stage analysis input, and the same thing we can access through load also. Load, construction stage, define CS, define construction stage. The same table will open here. Add. And here I'm giving the name as stage 1. Duration is 30 days. Now you can see this is what is the group name we created, and that group name will appear here. At the time, what is the age of concrete when we are activating the member at the site? For example, I'm giving you 14 days. And boundary conditions, these are the original support. I'm selecting the original condition. And the load wise, I'm applying the load self-weight at the first load case. And pre-stress I'm activating at that 14th day. Suppose it's the 14th day. And 14th day of first construction stage. 14, add. So this is the load cases and apply. And second, this is stage 2, same 30 days duration. Structure is already activated, boundary is already activated. Load is the SIDL I'm activating at the last day of second construction stage. Cross barrier at the last stage, we are doing it. And I'm creating one more stage. There is a stage 3 for long-term duration, that is for 10,000 days. There's no activation, so I'm just creating one load case for long-term loss calculation. See, all the loads are completed. Now we can just do the analysis part. It's showing element is not divided by, sorry, yeah, stage 1, the SG is not activated. This is the 14 days. Add is activated. Now we can see the analysis. Yeah, now the analysis is doing. Okay, now in the result part, first one is a load combination. We can do the concrete design combinations, auto design. Select the code. This is a static case and the construction stage. Click OK. This many load combinations for the service condition, strength and fatigue condition. And click OK. Now we can see the result part. The first one is the reaction forces. We can select any individual load cases as well as the load combinations. You can select any load combinations and value and legend. Click OK. So this is the reaction forces for the particular load combinations. And next is a deformation. This is a deformation contour for the same load combination with a deformed position. This is the forces beam diagram. You can select this, any combinations or individual load cases. MO is the bending moment. This is my bending moment value for the particular load combinations. It is showing that lane also. I will just display the lane. This is my bending moment for the particular load combinations. And then Fz is the shear force. This is my shear force value. Mx is the torsion values. So the three things we can see. And next is the stresses. This is a stress value. It is a beam. It is a beam model, so it's a beam stresses, and it's showing the combined stress, axial stress, shear stress, bending stress. We can select the component accordingly. And here the combined forces. And as per this reference picture, it is showing 1 and 2 are the top stress, the 3 and 4 are the bottom stress. We can see with the deformed also, and we can see how the stress is developing. We can see the animation as well. And close. So now this is the result part to extract the analysis result now. So this session, especially for making the modeling of a PSC structure, and we will organize more webinars on the design part next time. And this is the analysis with the live load and the pre-stress with the construction stage analysis. Now we can see the result in table also. We can see the reaction forces, like the load case or load combinations. This is the results of reaction forces. And next output is the beam is forces. We can select any load combinations. We can see the result for the axial force, shear, and torsional and bending moment. And next you can check the stresses. This is the stresses for any selected load combinations. And this table is we can export Excel sheet for the detailed the reporting work. We need the values in table. We can export Excel sheet. And next is we can see the tendon losses. So this is showing the number of cables. What are the number of cables which is there? The tendon name is showing over here. And the first column, this column is showing that force remaining in the cable after friction and slip. This is the elastic deformation loss, creep and shrinkage loss, and relaxation loss. We can check the result in the form of stresses as well as forces. Fine. So this is the modeling, analysis, and the result extraction in form of color contours as well as in tables. Yeah, this is the end of the session. Thank you.